This shouldn't be completely unfamiliar, but a relation is any mathematical relationship between numbers. Also variables or objects. Okay. And then you have functions, and we mostly deal with functions, and functions are special relations. Okay, every element in the domain, which is usually x's, only pairs with one element in the range. Which are usually y's. So if I plug in, say, 5 for x, so I take that 5, I plug it in, I'll only get one number out. I won't get two numbers out. Okay. Then we have descriptions for functions. There's a one-to-one function, an onto function, and then you have both. Okay, basically what one-to-one means is that every element in X goes to a unique element, or every element in the domain goes to an element in the range, but none of the range elements are used more than once.
Why don't you just skip C or
No, just to show that the range is not completely used up, because this one's not an onto function because I have extra elements left over in the range. But if it's not one-to-one, like maybe one here, one would go to D, and then maybe two would also go to D. But if it's one-to-one, that no range elements are used twice. So each range element is only used one time. So that's what makes it one-to-one. Okay. Onto is when every range element is used up. So maybe 2 x's or 3 x's or who knows how many x's go to a different range. So this is not one-to-one because both 3 and 4 go to C, but all of the range is used up. We don't have any left over that aren't being used. Does that make sense? Okay. And then if it's both one-to-one and onto, every element from D goes to a unique element in R, so there's no repeats for the R, and they're all used up. So we have no repeats and all used. And here we just have all used. Okay, when we're stating the domain and the ranges, remember that domain is x's and ranges are y's. So if I do my domain, that's going to be a list of all the x's. And my range is a list of all the y's. Now, if I've got the same number twice, I only list it once. Okay. To tell if it's a function or not, you guys remember every x can only go to, you can't have the same x going to two different y's, right? So none of these x's, like, each x goes to a different, we don't have the same x repeating going to two different y's. So it is a function. But do you see I'm using 9 twice? Or -9 rather. So it's not onto. Or sorry, it's not one-to-one. because the -9 is used twice. But if you look, if we were to make our arrows, every element in the range is being used, right? So it is onto. For our second example, our domain, we have 2, -1, -2, and then -1, and then 2 again. And then for our range, I have -2, -1, 0, 1, and 2. Okay. If I make my arrows for my pairs, see how these have 2 coming off of them? This is not a function. And the reason it's not a function is because if I have my domain and my range, 2 goes to both -2 and +2, and then -1 goes to both -1 and +1. And this is not okay. Your functions, your domain can only have 1 arrow each. The range, it doesn't matter. The range elements can have as many arrows as they want, but the domain can only have 1 arrow each. So that's what makes this not a function. And since it's not a function, I can't say if it's 1-to-1 or onto, because that's only about functions. Sort of like when we were talking about the degree and leading coefficient, if it had more than one variable in it, you can't say. Okay, so now we have continuous versus discrete. Okay, continuous function is, if you graph it, the graph is a line or a curve. And with continuous functions, the data points flow into each other. An example of a continuous function might be if I was measuring the amount of gallons in a swimming pool as I'm filling it up over time. Well, I'm not going to, I mean, I guess I could take a gallon-sized bucket and fill up the bucket and then dump 1 gallon in there. And then fill up the bucket and dump another gallon in there, and then that would be discrete because it would be 1 gallon, 2 gallons, like instant gallons. But that's not really how we fill up a pool, right? We throw a hose in there, turn the hose on, and come back in a few hours. So it's continuous function because the water is gradually increasing over time. It's flowing. A discrete function happens when the graph would be a set of individual points. Okay, the data points don't flow into one another. Okay, an example of that is if I went around every classroom up here and I counted students. And then I graphed it. Well, if this class has 20 students in it, the next class has 21 students in it, the next class has 10 students in it, those are not going to flow into each other because we don't have like parts of students in between the classes flowing into one another, right? There's not like a big giant pieces of student soup out there. It's individual numbers, so those would be discrete. So a graph of a continuous is going to be like a line. And a graph of a discrete function, it might look like a line, or it might have random dots everywhere, but it's just going to be a bunch of dots. Vertical line test is a test of a function. So you can test if something is or is not a function. If a vertical line only touches a graph once, it's a function. If it touches more than once, it's not. So if I have some random line or curve, and I take a vertical line, oops, and I take that vertical line, so pencil works, or the edge of your paper, and if I move it across, as you can see, each place I move it, it's only touching the graph in one spot, right? There's no place where it's going to touch the graph twice. So this would be a function. Whereas if I take that vertical line and as I move it across the graph, you can see it's touching in 1, 2, 3 places. So 1, 2, 3. So that's not a function because it's touching more than once. It's the length of a race each year. They have one race a year, and it has a different length each year. Is that discrete or continuous? It's going to be discrete, right? Because it's not like flowing, right? So this is a discrete graph. Okay. Then we're going to make a vertical line. Or use your, your pencil or something. And as we move the line, right there. Okay, as we move the line, if I look at this, is it touching more than one point at a time? So it is a function. Which makes sense, right? Because they wouldn't have 2 different races on the same year of 2 different lengths. It's the Tour de France. They only do that once a year. All right, graphing relations, okay? So remember we have our good friend y equals mx plus b, where m is the slope and b is the y-intercept. So in this particular graph, our slope is 1/2, and our y-intercept is -3. Slope is rise over run. Okay, it's positive 1/2. That means I'm going to go up 1 over 2. If it was negative, I'd go down 1 over 2. So positive means you move up, negative means you move down. Okay. So to graph this, first we need to give ourselves an x and y axis. We're going to start at our y-intercept, which is -3. Okay. from there, we're going to count up 1 and then over 2. And I'm going to do that a few times just to give myself enough points to draw a nice line. So start here and then go up 1 over 2. And then connect my dots. All right, so now we need to tell me the domain and the range. Okay. It has arrows on both ends, right? So it's going to go forever right and left. But it's also angled, so it's also going to go forever up and down. Do you guys agree? Okay. So my domain is all real numbers, and so is my range. All real numbers. Questions on that?
Are those R's?
Yeah, that they're like a R with a double. That indicates it's a real number when you put the two little lines. Okay, now we want to know, is it a function? Well, will it pass the vertical line test? Yes, so it is a function. And then we want to decide, is it one-to-one onto both or neither? If I look at just various x values, if I'm going along this line, at this x I only have one y, at this x I only have one y, this x, one y, etc., forever and ever. Are any of my y's coming from two different x's? No. So it's one-to-one.
Yeah.
And since I'm going forever in both directions, aren't all of my y's eventually going to get used up? So it's both. It's one-to-one. Because every y from only one x, right? Each y is only being used once. And then it's on to, because it's infinity, it'll go from negative infinity to positive infinity, and all will get used eventually. So it's both. One is independent, one is dependent. The independent variable is the variable that has freedom. Okay, this is our domain element, or our domain variable. So it's usually an x, and it can be chosen, or sometimes it happens by chance. Okay, but this is the one that this is the free one. This is the one that gets to be whatever it wants to be, whether that's been chosen for it or whether it just happens by chance. For example, if you are, let's say, well, let me explain dependent variable, then I'll give you an example that'll give you both. Okay. The dependent variable is the variable that has no freedom. It depends on the other choice. Okay, it's the independent variable, or I'm sorry, the dependent variable, whatever the independent variable ends up being, say it's a 5, then the dependent variable now becomes whatever it is based on 5. The dependent variable can't just be whatever it wants. So, for example, let's say you're buying fruit. And we buy fruit by the pound, right? Well, the number of pounds you buy is the independent variable. You know, you get to pick that. You go, oh, I want this many grapes, or I want this much apples, or whatever. You pick that. How much it costs is the dependent variable. Because when you get that bag of grapes and you go up to the register, the cost of the bag of grapes depends on how many pounds are in the bag. Does that make sense?
Yes.
And like I said, sometimes you get to pick. So if you're buying apples, you say, I want 5 apples. You pick. But you know, if you're buying a bag of grapes, you know how they have the bags already set up for you and you just grab one, and sometimes there's like 1.5 pounds in there, sometimes there's 2 pounds in there. You know, sometimes it's by chance. But the dependent variable is always based off of that. Using function notation, we looked at that a little bit because we, skipped to chapter 6. F of x is replacing y. And this f of x can only be used for a function. So if you see function notation, g of x, f of x, h of x, whatever, you know it is a function. You don't have to test it at that point. That's right there telling you this is a function. Here you go. So if, for example, we had a linear equation y equals 2x plus 1, in function notation, that would be f of x is equal to 2x plus 1. Same exact line. It's just we're writing it a little different. We're saying it's a function. And we know a straight line is a function because we just did one. Okay. We're going to do some more of these. I know you love them. So if g of x is going to be 0.5 x squared minus 5x plus 3.5. G of 2.8, we're going to plug 2.8 in everywhere there was an x. Then I'm going to square it and multiply it. And then I multiplied those and I added these. And then finally I add the last two. So this gave me that, those gave me that, those gave me that, and those gave me that. If I want to do g of 4a, well, I had g of x. And I replace x with 4a. Okay, remember when I have an exponent outside and I have more than one inside, I have to square both. So that's 16a squared minus 20a minus 3.5. And then I multiply and I get 8a squared minus 20a minus 3.5. Okay, linear relations. If it's linear, it gives you a straight line. If it's nonlinear, it's not a straight line. Very simple. Okay, a linear equation is an equation that contains only addition, subtraction, multiplication, and division of a variable by a constant. Okay. No variables can be multiplied together, so you can't get any, like x, y's in there. No exponents on a variable. So no, x squareds, x to the thirds, nothing like that. There can be no variables in a denominator. Or under a radical sign. Radical is like a square root. Okay. So if you're linear, you can't have any of those things. Okay, a linear function is just a function that graphs a straight line. So it's of the form like y equals mx plus b, except of course we replace y with f of x, and m and b have to be real numbers. These are linear. I have x's and y's, but they're not being multiplied together. None of them have exponents on them. None of them are in a denominator. None of them are under a radical. Okay, these are not linear. The first one because of an exponent. The second one because of the radical. The third one because x and y are being multiplied together. And then the last one is because of x being in a denominator. You can't have any of those things. So if you're ready, number one.
No.
Yes. Because the x is not in the denominator. Number two is no, because x and y are multiplied. 3, no, because x is in the denominator. 4, no, again, x is in the denominator. Yes, and no. Okay, so how tall is the sample after 3 days? Well, f of x was 5.9x plus 3.25, right? Well, if we want to know 3 days, that means we want to find f of 3, because x is the number of days. So you do 5.9 times 3 plus 3.25. Yeah, I really think that was supposed to be 0.59. I think I typed it wrong.
So we have what, like ridiculously long grass?
Yeah, ridiculously long grass. So Oops. Anyway, 5.9 times 3 is 17.7 plus 3.25. So at the end of 3 days, according to this, it would be 20 inches long. Obviously, that's not,
It's almost 2 feet.
yeah, obviously I made a typo. It should have been 0.59, but that's okay. The steps are the same.
It's like my dad's backyard.
Yeah.
After like 4 weeks.
Okay, so the term 3.25 in the function represents the height of the grass when measured initially. The sample is how many times is tall after 3 days. To find out how many times as tall something is, we take the new height and we divide it by the old height, and we get 6.4 times taller. Again, not in 3 days. That'd be some crazy grass, but the steps are the same,
Do like any feeding
right?
on your grass.
Okay, we want to find out how many days it's been since it was last cut if the Bermuda grass is 50 inches tall. Well, that would mean f of x is 50.45. So we plug that in. Okay, we're going to subtract the 3.25 from both sides. And we get 47.2 is equal to 5.9x. And then I'm going to divide by 5.9. And x would be 8 days. Again, obviously, no, grass is not 50 inches tall in only 8 days, but the steps are in the right order. ax plus by equals c. Okay, a, b, and c have to be integers. Okay, so no fractions, no decimals, and a is positive. B and C, it doesn't matter, but A has to be positive, and you can't have any fractions or decimals in the standard form. So, what we do, if we want to turn this into standard form, the first thing I want to do is get rid of the fraction. And in order to do that, I multiply by the denominator. So I'm going to multiply this whole thing by 10. And that's going to give me negative 3x is equal to 80y minus 150. Okay. The next thing I want to do is I want to have the x and y on the same side, right? Because I want it to be something x plus something y equals some number. So the second thing I need to do is have x and y on same side. Okay, so I'm going to subtract, or I can pick it up and move it. But if I move it, I have to change its sign. So I have 3x is minus 80y equals negative 150. And finally, A must be positive. Okay, it's negative right now, so I'm going to change all signs. So this will become 3x plus 80y equals 150. Okay, 3 is A, 80 is B, and 150 is C. Aren't that difficult. I want to put 2y equals 4x minus 5 in standard form. So I'm going to move this 4x over so it's on the same side as the y. Unfortunately, that's going to make it negative. But it can't be negative because it's the x, so I have to change all the signs. and then I have A, B, and C. And the x-intercept is where the graph hits the x-axis, and the y-intercept is where the graph hits the y-axis. Now, not every line will have both, but most lines will. To graph using the intercepts, you're going to find, well, first you need to find the intercepts. To find the x-intercept, you plug in 0 for y, and then you solve for x. To find the y-intercept, you plug in 0 for x, and you solve for y. So the first thing I'm going to do is I'm going to put this into standard form. So I'm just going to move that 12 over, and that makes it negative. So I just moved it. Or you could say add it to both sides, however you want to look at it. Okay. To find the x-intercept, I plug in 0 for y. So I get 2x equals negative 12. So x equals negative 6. And then to find the y-intercept, I plug in 0 for x. So I get negative 3y equals negative 12, not 13. Divide by negative 3, and y equals positive 4. Intercepts work best when C, this one, will divide by both A and B evenly. You can do it at any time, but it works best if they divide evenly, because then it's nice and pretty and fun. Okay. So first I need to give myself axes, which should actually be on a line. So give yourself an x and y axis. The x-intercept is negative 6, so I go to negative 6 and I put a dot. The y-intercept is positive 4, so I go to positive 4 on y and I put a dot. And then I connect the dots. Questions on that? Okay. If there are no questions on that, your homework is page 65, which is section 2-1, 9 through 31 odd. And that's for 11 points. Or page 72, and page 72, which is 2-2, 17 through 43 odd, and that's for 13 points.